Hi, my name is Naoki Iwayama and I present our SAS20 paper Predicate Abstraction and CEGAR for nuHFL validity checking. This is joint work with Naoki Kobayashi, Takeshi Tsukada, and Ryota Suzuki. In this work, we developed a method of automated nuHFL validity checking problem. nuHFL is a higher order logic with integer and greatest fixed point. It is equivalent to model mu calculus extended with higher order and integer and then restricted least fixed point. It is also equivalent to higher order extension of CHC. So it can be applied to various functional program verification. We also implemented validity checker based on the proposed method and evaluated it. First, we introduce the background of our work. As already said, nuHFL is a higher order logic with integer and great fixed point. It has lambda abstraction, application, and predicate over integers and greatest fixed point. nuX.psi is the greatest fixed point of lambda x.psi, so it is equivalent to the substitution of x in psi with the fixed point itself. As an example, let's see this formula. By applying this rule, we have this equation. Here, x is replaced with the fixed point itself. By beta reduction, we have this. We can see that the first line and the third line has the same subformula, so we can expand it again and again. So the meaning of the formula is for all non-negative even number n, p of n holds. It is known that nuHFL validity checking problem is equivalent to higher order extension of CHC satisfiability problem. So it can express various properties of functional programs including safety and non-termination. Let's see an example of safety verification. The program in the left side is a functional program that calculates the summation from 0 to n and asserts that the result is greater than n. We can translate the program into the nuHFL formula so that the program does not fail if n only if the formula is valid. Let's look into the details. Recursive function sum is translated into greatest fixed point sum. In the body, if then else expression is encoded by combination of the conjunction and the disjunctions. And then branch k of 0 is translated as it is, and so is the else branch. A third expression is also translated as it is. Like this, nuHFL can precisely express the property of the functional programs. The advantage of the nuHFL based verification is that it provides us uniform approach to various functional program verification including safety and non-termination. This is in contrast with Horus method, for example, which uses different algorithms to each property. Furthermore, though it is future work, we can deal with much wider class of properties in the same manner by extending nuHFL with these fixed point operators. This is the background of this work. Okay, so let me explain our method. Our method is based on predicate abstraction and counterexample guided abstraction refinement, or shortly CEGAR. Predicate abstraction is a technique of approximating integers by Boolean, and CEGAR is a technique of repeatedly improved abstraction using counterexamples. Let's see an example. Let psi be the formula shown in the previous slides. As an initial predicate, we use this one, which means that the argument R of k should be abstracted using the predicate R no less than n. The result of the predicate abstraction is this formula. Here, k of true corresponds to k of 0 here, and true is derived from the fact that the R no less than n is true, and n no greater than 0, and R equals to 0. Right hand side is also abstracted in the same manner. Since pure nuHFL validity checking is decidable, we can automatically check whether phi is valid or not. In this case, it is valid, and because abstraction is done in sound manner, we can conclude that psi is also valid. So we've finished nuHFL validity checking. In this case, we started with good predicates R no less than n, but we cannot always choose such a predicate beforehand. So in general, we should start with empty predicate set. In this case, the result of the predicate abstraction is this formula. And because it is so imprecise abstraction that the result of the abstraction is invalid one. When phi is invalid, nuHFL validity checker generates information called a counterexample. It is a subformula of phi that witnesses the invalidity of phi. Given counterexample, we check its feasibility by calculating corresponding subformula of the original formula psi. Unlike most CEGAR algorithms for programs, the counterexample is a tree-structured formula, not a single execution path. So we need a more elaborated solution. Infeasible counterexample means that the abstraction was imprecise, so we have to refine abstraction. In this phase, we find a new predicate using the information of counterexample. We skip the explanation due to the time constraint. But if we can find a predicate R no less than n, we can prove the validity of psi as already explained. Next, let me explain what was the challenge in our method. Challenges lie in both predicate abstraction phase and CEGAR phase. In predicate abstraction phase, we need to track the relationship of predicates like one of the two predicates always holds. In CEGAR phase, we need to deal with tree structures counterexamples as already said. So more elaborated solution is required. In this talk, we will talk about the former challenge. Given nuHFL formula psi and predicates, the goal of predicate abstraction is to calculate pure nuHFL formula phi that and approximates psi. Let's consider abstracting this nuHFL formula using these two predicates. In our method, integer arguments are abstracted into Boolean arguments. When this function is called, true is passed only if x greater than 0 or y greater than 0 holds. So this abstracted formula semantically corresponds to this nuHFL formula, which is an approximation of the original formula. So let's see what is the challenge about the predicate abstraction. Consider abstracting these three formulas using these three predicates respectively. F and Z are abstracted into the identity function since the predicate is the same as the body of the formulas. So what will be about H abstracted using no predicates? If we abstract H in a negative way, we have this formula. That is because true can be passed only if predicates x greater than 0 or x no greater than 0 holds, but we have no information on x as the body of x since it has no predicates. As a result, the abstracted formula is invalid, the original formula h of x is valid. However, by focusing on the fact that one of x greater than 0 and x no greater than 0 is always true, this abstraction is also possible. And this one is valid. We carefully designed the abstraction rule to achieve this kind of abstraction. We can now explain how the example sum is abstracted. And this is the abstracted formula using predicate r no less than n. This formula is also consists of two parts, case for n no greater than 0 and n greater than 0. Each part corresponds to the original formula. For the former case, this true is derived from the fact that r no less than n is true under n no greater than 0 and r is equal to 0. In the latter case, this p is related to r prime no less than n minus 1 since it corresponds to the recursive call for n minus 1. So we can apply k to b here because R no less than n is implied by R prime no less than n minus 1, and n is greater than 0, and R is equal to n plus R prime. At last, by simplifying the formula, we obtain this one I showed in the method overview. We also show some desirable properties of the proposed method. For predicate abstraction phase, we showed soundness and completeness with respect to refinement intersection type. The latter means that if psi can be proven using refinement intersection type, it can be also proven by using our predicate abstraction. In other words, our predicate abstraction is at least as powerful as refinement intersection type system. For CEGAR, we showed the progress property, which means that the same counterexample never appears twice in the CEGAR loop. Based on the method explained so far, we implemented a validity checker and conducted two experiments. First, we compare our validity checker with Horus developed by Van et al. Horus is a solver of higher order GH satisfiability problem, which is equivalent to nuHFL validity checking problem. Both benchmark A and B are made of program verification problem. Benchmark A is written by the author of Horus and B is written by us. The results said that our tool can solve more problems than Horus, while Horus is much faster than ours when it succeeds. Second experiment is comparison with program verification tool MoCHi. It supports both safety and non-termination verification, but uses different algorithms, so each algorithm is more specific than ours. The results showed that our tool is competitive with MoCHi in terms of execution time, while it can solve less problems. So in conclusion, we propose a new method for automated nuHFL validity checking problem. It is based on predicate abstraction and shared and has good properties like soundness, completeness with respect to refinement intersection type, and progress. We also implemented a validity checker. Our validity checker outperformed Horus in terms of precision and is competitive with the more specialized program verification tool MoCHi in terms of the execution time. Thank you for listening.